run, and then I sleep through my alarm and I actually miss the class.
Do you know if this presentation is going to be made available online?
It is.
Or it is already online?
It is not online yet.
But it will be.
It will be.
I'm good at it. I'm good at it.
There, your simulation's done.
Okay, so just for reference, for Paul's sake, those of you that are working on the ROMS project, please raise your hands. Okay, there's your target.
Okay.
So Paul said that he'll give us the slides that he's going to present today, and I'm recording it so that people can go back and review it if necessary. And I'll post this on my faculty website, so you guys can review it later if you choose to do so. But since we're already 5 minutes in, I'll let you take over the show.
Okay.
Thanks.
Sure. You're welcome. I wanted to say, first of all, thanks for those of you who are willing to jump into this ROMS project. I feel like I'm going to get a lot out of this as the end user. So thanks off the bat. And also, this presentation isn't very polished. I just threw it together over the last few days. So we'll kind of go through, and I'll try and indicate where things might help you out. I'm trying to anticipate what problems you might already be having, just starting up from scratch. The people who develop ROMs, so I didn't actually develop the code, but people who have developed it hold workshops annually, and it's like a week-long workshop to learn how to use ROMs. So we'll try and hit on all the main points just to get you up and running. And please ask questions. Because like I said, I did my best to anticipate what problems you might be having, but if I'm not addressing your biggest frustrations, then by all means speak up. Okay, what is ROMS? It's a finite difference code that simulates the ocean. It stands for the Regional Ocean Modeling System. So it models the ocean. So I'm going to talk about what it computes. What are the main files you need to worry about? There are hundreds of these files there. 99% of them you don't have to touch. So all of the Fortran files you probably don't have to tweak at all. So which input files will you probably have to play with to make sure that it runs without crashing and that kind of thing. And you know, if you set the parameters wrong, it can crash. So it's important to be aware of. And so how do you work it? Well, there's like a default setup, the simplest possible setup. It's called the upwelling run. And I recommend getting up to speed on that first. If you can get that running, then transitioning to these more complicated setups are relatively straightforward. And this, when I typed this up, it was supposed to be phrased, "Oh yeah," like don't forget the last little thing. But on paper, it looks like, "Oh yeah." So you can read it either way. But basically, when your daily cycle of I'm going to compile it, I'm going to run it, I'm going to do some tests, I'm going to change something, I'm going to compile it, I'm going to run it again. That cycle, there's only certain files you play with, but before you do that at all, there's a bit of headache setup stuff. So I'll mention the things you have to do first. I'll mention that at the very end, because it's not sort of the typical day-to-day of it. Okay, so first some words. It's a regional ocean modeling system. It takes these partial differential equations, and I'll show you the partial differential equations in a second, but you don't need to know what they are. It models these equations of motion, these dynamics, to simulate the ocean. When I say simulate the ocean, what does it have? It's got velocity, the u and the v, the two components of horizontal velocity. It's got temperature and salinity, because those two together with something called an equation of state give you density. And density of the water with gravity, you get the water sloshing around. And it can model the sea surface elevation. So there's the 5 variables, the UV, temperature, salinity, and sea surface height. Of those, the 4, the UV, temperature, salinity, are 3-dimensional. Sea surface height is just sort of how high the surface water is. So if you've got like a tides coming in or going out, so the waves on the surface of the water. What do you need to do? You need to feed it the initial conditions. So what are all these variables at the initial moment? And what are those variables on the boundaries? And how is the wind forcing things at the surface? And the equations of motion properly take this forward in time. So it takes all these variables forward in time. And these initial conditions, boundary conditions, and wind forcing, they could be specified internally, and that's the most simple setup, this upwelling setup, or as external files, and if you're going to do some realistic runs, it's got to be this external file setup. And basically, here's some more buzzwords, in case this means stuff to you, but you probably won't have to sweat this at all. It's a finite difference code, so it takes these PDEs, and it's got this fixed grid, and so it's a finite difference code, so it's not finite element, say, and it's not spectral, say. Staggered grid is this thing that means that where the U points are is a slightly different place than where the V points are. That's a technicality you need to worry about if you're going to plot up results or if you're going to compute something based on the U's and the V's, like compute like a net volume flux through some imaginary window. So if you need to play with the code further, you might be confused if you look into it. So be aware that the U points and the V points and the density points are all kind of slightly staggered relative to each other, and that's to make the finite differencing work properly. In the horizontal, it's just a regular crisscross grid. In the vertical coordinate is some fraction of the local depth. So there's, in shallower water, there's higher resolution, then in deeper water, it's you go to like a depth of -1 up to 0 in this sort of this vertical, this terrain following coordinate. And something else that sometimes you need to keep aware of is when you find a difference and you set a delta x, you set a delta y, and you just set a delta t. And it turns out a clever way to do the delta t when you're simulating the ocean is to have two versions of the delta t. One delta t is to not let the sea surface elevation move along. You got these waves, and it turns out the waves on the surface move much faster than the waves inside. So if you imagine a bottle of salad dressing with oil and water, if you kind of shake it, the surface moves around fast, and the inside, like the internal boundary between the oil and the water, moves slower. So there's two time steps, one for the internal, so-called the internal time step, that's a longer time step, and then the external time step is it's a faster time step, which just advances forward in time the depth integrated equation of motion. Just it models how the sea surface waves move around. You got to keep that in mind because if you increase your grid resolution, your time steps have to go down. And I'll show you where in one of the output files it tells you if your delta t is too large. You need to make delta t small enough so that the waves aren't propagating too fast for your grid. So that's, in a nutshell, what's going on. You're simulating the ocean. What are the files you need to worry about? There's something called a build.bash or build.sh, depending on whether you like the bash shell or the Bourne shell or the C shell, whatever. So there's a shell script which internal to there, it sets all these different folders, and it calls the make file. So you compile through this build bash, and I'll show you an example. There's an ocean.in, or you can change the name here, but .in file is a text file with just input parameters that tells the delta t and the delta x and how many grid points. And that you need only at runtime. You don't have to. You can change that after you compile. There's something called a header file, which you probably won't need to change, but as a scientist, you change this a lot because what this does is it tells the compiler which parts of this big monstrous code to put in. So you can keep out parts of the equations of motion and say, well, let's pretend that the Earth isn't spinning. What effect does that have? Or let's pretend that the sea surface height doesn't move. And so this tells you what the effect of the different terms in the equations are. So in this so-called header file, there's a C preprocessing option that when it does the build.bash, it first parses the code with a C preprocessor, and it builds parts. It builds the code out of like a super code, and this part turns on and off compiler switches. So these are kind of input files. You basically need to worry about the ocean.in, and you compile it with this build bash, and I'll show you in a second how that goes. Output, it outputs a lot of files. The most important one is this ocean_his. It's supposed to be the history of the ocean. So it's the U, V, T, S, and the sea surface height at each grid point at specific times. And you say in ocean.in which times you want it to output. And it also outputs a bunch of stuff to the screen, and you can put that into a log file. Let me show you. So this is the default simplest upwelling run. How does it what would you do to compile it? Well, you would set up, you go into this build.bash file, make sure everything's teed up correctly, and you set up your ocean.in file, make sure everything in it is set up correctly. You compile it with this command, and you run with this command. And it spits a bunch of stuff to the screen. And if you want to save all that stuff spat out to the screen, you can do something like this. You can input your text file into your executable. This is all in a Unix sort of environment. Put it into the executable, and then spit it out into your log file, and then ampersand so that you can log out and walk away and go, and it still runs in the background. Let me give you just a rough idea of what that might look like. So if I go into this, I've done an upwelling run. This is just on the laptop. You're going to run ROMs on a laptop for this upwelling run because it's coarse resolution and things work. So then you see there's this ocean_his.nc, and there's things like ocean_dia for diagnostic, and average, which averages the variable's history, gives you snapshots. RST is for a restart. That means if you do a run and it takes a month for you to do the run and it doesn't quite get to where you need it to go, you can restart from where you finished. For you guys, you probably won't need that. So the ocean his is the main output. And there's this log.txt. But so let me show you sort of what the main. I guess when I first started doing ROMs, I was really baffled by what's my basic cycle of commands, please. And no one did this for me, so I wanted to say, look, when you can go build bash, and what you'll see when you go through, if things are working right, what you'll see is something like this. This is compiling right now as we speak here on my little laptop, and so you'll see it goes through all these things, and it does the C pre-processing stuff. So this is all good, and so let me show you as that's going. Just to give you an idea of the equations of motion, I don't know. So don't sweat about it too much, but they're partial differential equations, and it's conservation of momentum, and there's a Coriolis term for the spin of the Earth, and there's a pressure gradient term, and there's some fancy stuff in there to model the turbulence subgrid scale. So it's, even though it's finite difference, which isn't that highbrow, they're using the best sort of finite difference schemes. So there you have a U component, a V component, and C is generic for tracer, so it's temperature or salinity. It just gets dragged around by the flow. And there's viscous terms, whoops,